Hi guys, this video is the second of two over section 6.5 hypothesis testing. These notes are posted on Brightspace, and this time they're all filled in, so you won't have to write anything, but maybe following along will be helpful. That'll speed things up a little bit. Let's just jump to an example. So a fishing lodge advertises that the mean weight of bass in its lake is 4.5 pounds. A sample of 40 bass that we actually catch shows a mean of 4.2 pounds and a standard deviation of 1.1 pounds. So the mean of our sample is less than what the lodge was claiming, and we're trying to check, do we have sufficient evidence to doubt the claim of this lodge? And specifically, the question is phrased, can we conclude that the mean weight differs from 4.5 pounds? So let's see if we can do the problem. N, our sample size, is 40. That's bigger than 30, so the sample mean will have a normal distribution, and we're good to start our calculations. First step, let's identify the hypotheses. So this is a test for a mean. We're just trying to discuss something about a population mean. So maybe a note to myself that mu in this problem is going to stand for the mean weight of all bass in the lake. And then for our hypotheses, if I jump to the alternate hypothesis and say, what is the question asking me to check? Does the mean weight differ from 4.5? So you can be different from by being bigger or smaller. So that indicates that we have a two-tailed test. Mu not equal to 4.5 is what we're trying to find evidence for. And the default is to take the fishing lodge at their word that the mean is 4.5 pounds. The problem also tells us that the significance level that we should use is alpha equals 0.05. I don't need this to do a problem, but it helps to kind of see what's going on. Here's the X-bar distribution with a mean or peak at 4.5, and then 4.2 is the sample mean that we actually got. Now, this is a two-tailed test, and so I went down by 0.3 to get to 4.2. So if I take the mean and go up to up 0.3 to 4.8, that gives me a picture that shows what probability I'm trying to calculate. To be not equal to 4.5 is to be far away from 4.5, either this far away from 4.5 in the left tail or this far away in the right tail. So we'll calculate that probability in a moment. First, let's convert to a t variable so that we can use an Excel command. So I take the sample mean, subtract the notation mu0 is just referring to the number that's being compared with in the hypotheses. And then this is the standard deviation of x bar, s divided by square root of n. So I plug in the numbers, 4.2 minus 4.5 and 1.1 over square root of 40. And I get that t is negative 1.72. So now I can write the problem in the same way, just in a different variable. Here's a variable t. A t-distribution always has its mean or peak at 0. And here's negative 1.72, here's positive 1.72, and this blue area that I have shaded is also what I'm trying to calculate. It's the same thing as the red area up here. So the p-value is the next step. That's the sum of these two areas, either the probability that t is less than negative 1.72 or that t is greater than 1.72, and I add the two areas to get the total p-value on a two-tailed test. But notice that the t-distribution is symmetric, and so this second term is the same thing as the first term. The area in the right tail is the same as the area in the left tail, so I can just find the area in the left tail and double it. Regarding and there should be a negative sign right here. Oops. Should be a negative sign right there. Okay, regarding the Excel command, t.distribution is the appropriate one. So here's my 2 times t-distribution negative 1.72. And then the next thing that this command wants is the sample size minus 1, 40 minus 1. And it's true that we're looking for an area. And Excel gives us that that is 2.093. So finally, I'm ready to make a decision. As always, I compare the p-value with my level of significance. This p-value is larger than alpha, and so it's saying this probability is big enough to be believed. I will not claim that I have evidence for the alternate hypothesis. In other words, don't reject the null hypothesis. And then finish with some sort of English statement that indicates what's been decided. At 0.05 significance, there is not sufficient evidence that the mean weight of all bass in the lake differs from 4.5 pounds. Notice that I'm again stating the conclusion in terms of the alternate hypothesis. And I should probably give my test statistic and p-value. So t equals negative 1.72, p equals 0.093. Okay, it would be fine for homework like this to actually just write it on a piece of paper and scan and upload to Brightspace. If you want to do it on Excel, it's a little clumsy because it's hard to type these symbols. So let me show you what you could type. I'll move this over here so that we can see that at the same time as my Excel work. So here's how I might do my homework if I were doing it on Excel. I could say that n equals 40 is greater than 30. So x bar is normal. And then we're going to have a series of expressions here. So I'll make labels in column A and then their values in column B. I guess one more statement. Mu is going to be the mean weight of all bass in the lake. Now, I have a null and alternate hypothesis. The null hypothesis is that mu equals 4.5. The alternate is that mu is not equal to. So that's kind of clumsy to type, but you could do a less than greater than 4.5. The next thing is to calculate t. And I put a label for t, and then as far as the calculation, it was 4.2 minus 4.5, and then divided by 1.1 over square root of 40. It's really important that you get the parentheses correct here. So I want the subtraction to happen first, so parentheses around that, and then I want the division in the denominator to happen next, and then finally the overall fraction. I'm referring to this calculation right here. First compute the numerator, put that in parentheses, then the denominator, put that in parentheses, and divide. So here's my number, negative 1.72. Then for my p-value, the calculation or command to do that was 2 times the t-distribution and negative 1.72 and 39 and true. There was my 0.093. And finally, a conclusion at 0.05 significance. There is not sufficient evidence or significant evidence that the mean weight differs from 4.5 pounds. T equals negative 1.72 and P equals 0.093. This doesn't show everything, but enough of it, and especially if somebody wants to, they can look at the formula. So turning this in would be an appropriate amount of work if you want to do it on Excel. Or again, you can turn in a handwritten version that looks like this. Let's check out another example. This one's going to be for a population proportion rather than for a population mean. So let's get a little background on that before we go to the example. The notation here is the variable p by itself is going to stand for the population proportion, the proportion of successes in the population. If I put a bar over it, p bar refers to the same thing but in the sample, and as always, n is the sample size. The check for doing a hypothesis test like this is that in my sample, which is going to consist of qualitative or categorical data, just success, 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 fail, fail, success, and so on. I need to be sure that there are at least 5 successes and 5 failures. If so, then the sample proportion will have an approximately normal distribution, and its expected value will be the population proportion, and its standard deviation will be given by this expression. We've seen these before. So the right thing to do for a hypothesis test is to use a normal distribution. These size checks verify that, that this expression will have a normal distribution. So I take the sample proportion, subtract off the quantity I'm comparing to, and divide by the standard deviation. And just as with means, I can do any of 3 types of tests: a left-tailed, right-tailed, or two-tailed test, and they get their names from the form of the alternate hypothesis. And I see a typo here also. This should be a greater than right here. Here's the example. So here's a company, pharmaceutical company that manufactures sunscreen, and they test their own product and a competitor's product on 20 people. So they have test subjects apply the product and then expose their skin to the sun, and then calculate the relative protections or measure the relative protections. So the setup probably is, for example, in their left arm, they're putting the manufacturer's product. On the right arm, they're putting their competitor's product and then comparing the amount of sunburn. So out of the 20 people, the manufacturer's product in our test offered better protection for 13 of the people. That's more than half, but it's a small sample. We're trying to decide then, is there sufficient evidence to conclude that more than half of all people would get better protection from this product than the competitor's product? It happened in the sample, but would it happen in the population? We'll do our size checks. There are 13 successes, 7 failures. Both of these are more than 5, so I'm good to go. Set up hypotheses. So again, probably best to start with the alternate hypothesis. What exactly am I asked to check? Is there sufficient evidence to conclude that more than half of all people would get better protection from this product? So if P is the proportion of people who get better protection with this product, then we're trying to check whether P is bigger than 0.5, more than half. That makes the null hypothesis P less than or equal to 0.5, and our level of significance is 0.05. Next step, calculate the test statistic, it's called. In this case, it'll be the variable Z. So P bar in the sample, the proportion of successes I got was 13 out of 20 or 0.65. Then I calculate the standard deviation of P bar. So it was the formula we had on the previous page. And the P sub 0 number that I'm comparing in my hypotheses is 0.5, so I use that. The sample size is 20, and I get 0.112 as the standard error of P bar. So calculate now the test statistic, take P bar and subtract off the 0.05 comparison number and divide by the standard error that we just calculated and get 1.34. Now I can see what I want to do. On a z distribution, the peak is at 0. Here's the number 1.34 because the alternate hypothesis shows that this is a right-tailed test. I'm trying to calculate the area to the right of 1.34. So that's what I'm doing when I go for the p-value here. The probability that z is greater than 1.34. Well, I'm going to use a Excel command for the normal distribution, but they're all set up to give area to the left. So if I want the area to the right of 1.34, I'll take 1 minus the area to the left of 1.34. And an appropriate Excel command to use is norm.s.dist. This is the normal distribution, and then S stands for standardized, which means that it has mean 0 and standard deviation 1, actually. So if I use the .s command, I don't have to give the mean and standard deviation, just the number that I want the area to the left of and true to tell it I do want an area. The p-value then turns out to be 0.09. That's this area here. And I finish in the same way I always finish a hypothesis test, compare the p-value to the level of significance. In this case, again, the p-value is bigger than the level of significance, so we will not reject the null hypothesis, but we'll say at 0.05 significance, there is not significant evidence that the proportion of all people who would be better protected by this product is more than 0.5. I'm concluding the fact that we don't have evidence for the alternate hypothesis with our z equals and p equals numbers. So that finishes that example. And now I'd just like to spend a few minutes kind of talking about the things that can go right and wrong with hypothesis testing, just more general comments. Whenever you want to use a t-test, either for a mean or a proportion like this, keep in mind that the sample had to have been taken by random sampling. It's easy to forget that, but if we take a convenience sample, then no statistical analysis on that sample is any good. The sample is biased and none of the theory applies. And there should be some sort of size check. So if the sample is roughly symmetric, I'm talking about quantitative data now, or a mean. So if the sample is roughly symmetric with no strong outliers, I'm good to go. Or if the sample is large, say bigger than 30, I can just move ahead anyway. Second point, alpha equals 0.05 is almost always the level of significance that's actually used. And as far as the level of significance, again, that is the cutoff between probabilities that are too small to accept as chance and large enough to be attributed to chance or to be believable. Also, the p-value is the probability of getting results as extreme as we did. And so the decision rule for a hypothesis test is always like this. There are lots and lots of kinds of hypothesis tests that we won't talk about, but they all work that you compare the p-value to the significance. If the p-value is really small, you say, I don't believe the null hypothesis. That's too small of a probability to be believed, and you reject the null. If the p-value is greater than the level of significance, then we say, that could be believable. I won't reject the null hypothesis. Number 3, we've stated our conclusions like do not reject the null hypothesis. Well, why can't I just say I accept the null hypothesis? And that's the same question as saying Can a jury just say that the defendant is innocent? And they really don't. A jury only says not guilty. The jury never says the defendant is innocent. What's the difference? Well, to be innocent really means you didn't do it, and the jury can't and isn't required to decide that. The jury never knows for sure. That's why there's a trial. The jury's job is to say not guilty, which means that there's not enough evidence to convict this person, and therefore they should be treated as innocent. So it's better to say not reject the null hypothesis. Item 4, your hypothesis test can be left-tailed, right-tailed, or two-tailed, but you're really supposed to choose which it is before you look at the data. It's not good statistical practice to look at the data and then decide what you're going to try to show. Point number 5 is just a FYI, kind of interesting. The science of hypothesis testing is serious business. It applies to legal cases, actually. So there was a situation in Texas where juries the jury selection process seemed to be discriminating against Hispanics. And a statistical study showed that the odds of getting so few Hispanics on juries, if they were being chosen randomly, was really, really small. And this case went to the Supreme Court, United States Supreme Court, which ruled that a hypothesis test with enough statistical evidence can shift the legal burden of proof. What that means is a company, or in this case, a county, may have to prove that it's not discriminating rather than a plaintiff coming to court and having to prove that the company or government does discriminate. So that's a huge deal. To flip the legal burden of proof is really quite significant. Number 6, keep in mind that there's a difference between practical and statistical significance. So a while back we had an example from the bottling company. The company was claiming that they were putting in at least 32 ounces into each bottle of soda. And if we take a sample and get a sample mean of 31.99, and suppose we have a sample size really, really large, like 100,000 bottles in our sample. Well, it turns out that that's going to be enough evidence to reject the null hypothesis. If I have 100,000 bottles and their mean is just even a little bit less than 32, then I'll have enough evidence to say the mean is not really equal to 32. But does it matter? Does anybody really care if their soda bottles have 31.99 ounces in them instead of 32 ounces? Of course not. And so the point is, even if you find statistical evidence for a new result, an alternate hypothesis, that's not necessarily saying that it's important in real life. Finally, number 7, it can be shown actually that this number alpha, the level of significance, really is the probability of a type 1 error. And that's type 1 errors are bad, so we want alpha to be small, and the question then is, well, why can't we just make it really small? Why use alpha equals 0.05? Why not alpha equals 0.00001 or something like that? You should keep in mind a teeter-totter or seesaw like this. And it turns out what happens is if I try to reduce or do reduce the probability of a type 1 error, it's unavoidable that the probability of a type 2 error will increase. Probability of type 1 error is reduced, probability of type 2 error will increase. And type 2 errors aren't good either, so I have to get a balance here. I can't take alpha to be too large because then I'll get too many type 1 errors, but nor can I take it too small because then I'll get too many type 2 errors. It has to do with the level of evidence that you say you need before you'll make a decision. And we'll stop there.